Okay, so our sun, like other stars, creates its energy through nuclear fusion in its core. And so I would like to kind of give you a quick rundown as to what nuclear fusion looks like. But before we do that, let's talk about the two different types of nuclear reactions. Now, what these two types of nuclear reactions have in common is that they both deal with the atom's nucleus. Now, remember that we can think of atoms as being composed of three major subatomic particles. We have protons and neutrons in the nucleus of an atom, and then we have those cute little energetic electrons in a cloud outside the nucleus. Well, let's start with the first type of nuclear reaction called fission. Now, fission actually involves a large, let me see if I can bring up I don't have my stylus here, so this is just using the mouse, so it might be a little bit ugly. In nuclear fission, what happens is the nucleus, now you just have to kind of picture the electrons in a cloud outside this nucleus. These nuclei here are represented with two different colors because, of course, we have, I think it's the red protons and maybe the black neutrons in the nucleus of an atom. In nuclear fission, what happens is a large nucleus like this breaks down into smaller nuclei. And again, you just have to kind of picture both the large nuclei to begin with and the two smaller nuclei. They'd still have electrons in a cloud outside their nucleus, or outside the nucleus. But in this fission process, what ends up happening is if you would weigh what you start with, the reactant, and what you end with, the products, you would see that you're missing mass. And that missing mass then is converted to energy. This is an example of nuclear fission, and energy is released. You've probably heard of uranium power plants, and what they do is take, uranium has a nucleus that under certain conditions will go ahead and divide, or divide in a nuclear fission process, and it will create energy. So, but in stars and in our sun, what's happening is nuclear fusion. And in this case, nuclei are being fused or brought together. So, just in general, we can think of what's happening in our sun is hydrogen is fusing to form helium. And I'm going to kind of talk you through that. And by the way then, let's see, where's my little, there it is. By the way, again, if you were to kind of measure the mass of these two particles, these two nuclei, and compare it to the mass of this nucleus that was formed over here, you would be missing mass. Your product is lighter than your reactant, and that's the mass that is converted to energy according to Einstein's relationship during nuclear fusion. So let's focus on nuclear fusion, since that's what's going on in the core of our sun and the core of stars. So it's a tough thing, and now here we have two protons. This is the nuclei of two different atoms. It is a tough thing to get those two protons to want to stick together. Remember earlier in this chapter 10, I said that it's the sun's core that we can have fusion occur. And in the sun's core, we have high temperatures and high pressures. So this says that at regular low speeds, you're not going to get those nuclei together, okay, because they're going to repulse each other. High temperatures are what you need in order to get those nuclei to fuse together. And the process we call nuclear fusion, and during their fusion, energy is released. So at high temperatures, and how do I say this? The speed of matter, all matter has motion, and the higher the temperature that matter is, the more motion it has. So literally, at high temperatures, these things can have a lot of speed and run into each other. All right. So in general, I'm going to kind of break it down here even further, but in general, what's happening in our sun is that we have 4 hydrogen atoms, 4 cute little protons with electrons around them, but we're not worried about the electrons. In fact, I don't know, at that temperature they might be ionized, I guess. So we have 4 protons joined together to make four protons or four hydrogen atoms joined together to make one helium atom. So that's why we say in our sun what's building up right now is helium, where our sun is losing hydrogen and it's building up helium. And all stars start out that way. Notice, and I said that I'm going to kind of, Einstein said we can convert matter to energy according to energy is equal to the mass of the matter times the speed of light squared. Okay, so energy is released during this process. And that's what's happening in our sun. Now let's kind of break it down a little bit further. There's something called the hydrogen fusion by the proton-proton chain. Let's see what you think. But the net result is what you saw before. So for instance now, and actually we're going to talk more about this later, but this is a neat little figure that shows you particles that are released. And over here, you have to kind of see what those particles are. Can you see the little pink and the little kind of black and white thing? Okay, that is a neutrino, and that is a positron. Neutrino, positron, all right? Those are released early on in this fusion process. Notice then what we have here is actually deuterium. It's another form of hydrogen with one proton and one neutron. And then what happens is we add another proton to our deuterium. Notice what we get out is, this is energy, a gamma ray. And this energy will wiggle. Remember, this is occurring in the sun's core. This energy will work its way out to the surface of the sun and then will take off in all directions. So the end result of adding another proton, finally we have this particular form of helium. I know it's helium because we have two protons in the nucleus of these atoms. Then you take those two helium atoms, which is kind of an odd sort of isotope of helium, you merge them together and notice what you get back out. You get a couple of protons back and you get your normal helium. There's helium with two protons and two neutrons. Notice those protons can go ahead and start all over again. That's the kind of proton-proton chain. So kind of the overall, this is what we have going on. Notice that we take four, where'd it go? The net is 4 protons, and we get back, this is a helium nucleus, and notice all the other stuff that we get. We get neutrinos, 2 positrons, and gamma rays. So I just think that's a good summary. So another way, put another way, what we put in our ingredients are 4 protons. Now this happens again in the cores of stars where we have high temperatures and high pressures. And what do we get out? We get the nucleus of a helium atom, and we get 2 gamma rays, 2 positrons, and 2 neutrinos. And I mentioned before, if you compare the mass, the weight of your 4 protons versus the mass associated with what you get out, you have lost 0.7% mass, which seems like quite a bit. And that's the mass that's converted to energy. So this is kind of a cool thing. Let's see, I'll kind of talk you through this. You see the arrow. So for instance, if we have a slight drop in the core temperature, what will happen is that the fusion rate will decrease, because it just will. And as the fusion rate decreases, what will happen is that that the pressure will lower and the core will contract, and the core contracting will go ahead and make it heat up again. So decline in core temperature causes fusion rate to drop, so the core contracts and heats up. Put another way then, if you have a rise in core temperature, it's over here, okay, then you're going to, your fusion rate will increase, your core pressure will rise, and your core will expand, and then your core temperatures will fall because your core expands. So in this sense, the sun's core, just as the core of other stars right now that are in what we call a nice kind of equilibrium situation, kind of has its own thermostat where it won't overheat. So I didn't mention the time, but it takes, I've read, like 170,000 years. I think 170 million years. I'm going to have to double check that. For a certain amount, for any sort of energy that's created in the sun's core to wiggle out to the surface of the sun and then find its way ultimately to leaving the sun. We said that there are, after the sun's core, the energy needs to work out of what we call the radiation zone, and that's kind of what's shown here. At the top of the radiation zone, we have the convective zone. And so this is showing you the convective zone here, where we have, it's hot gas. I finally read my slide. It's hot gas rising, okay, and then it sinks. And then it heats up again, and it rises, and it sinks. Okay, that's a convective zone. And so in that way, the sun is working its thermal energy, or its energy outward. So actually, as it turns out, these kind of little cells, these little convective cells, which probably aren't so little if you get up close to them, are a surface feature that we call on the sun called granules. These are solar granules, and they kind of look like honeycombs. And we're going to talk about in a minute, in a little bit, in this chapter anyway, about the sun can be active or the sun can be quiet. And features of an active sun actually kind of come and go. But sun granules are always there. So how do we know what's going on inside of the sun? One of the ways is by spacecraft. The spacecraft, which I'm going to take you to the website called SOHO. It's the Solar Observatory Solar and Heliospheric Observatory. There you go. And I read a little bit about this particular spacecraft. It's pretty cool. What it does is it is in Earth's orbit about the sun. So it's kind of in a stable position, and it precedes the Earth in the Earth's orbit. So as we orbit the sun, so also does the SOHO. It was put up in 1995, which seems like a long time ago, doesn't it? And it's still giving us images. There are other spacecraft out there observing the sun too. So we learn about the sun by making mathematical models, observing solar vibrations, and looking for those cute little tiny subatomic particles called neutrinos. Remember when we talked a few slides ago about nuclear fusion in the sun's core, we said neutrinos were kicked out. So the vibrations of the sun actually we can map them, and they end up it's like a very beautiful symmetrical sort of thing. And if you know what you're looking at, vibrations can tell you information about the density of the matter and the nature of the matter on the inside of the sun. So what you're looking at is a dotted line that's the predicted model, and the real data is the solid kind of orange line, and they are very much overlaid. The two parameters to kind of look at, do our models agree with the data that we observe, is the temperature of the sun, the internal temperature of the sun, and the density of the material inside the sun. So the way you read this then, we basically have a couple of graphs going on here. Oops, I was going to kind of do this. We have a couple of graphs going on. The top graph is temperature, the bottom graph is density. And both of them basically go from the core out to the edge of the sun. So it's got the highest temperatures in the core, and it's got the most density in the core. And as you might imagine, as we go out, and remember, around the core is the radiation zone or the radiative zone. Okay, as we go outward, both the temperature drops and the density drops. And then we get to the convection zone, and again, the temperature drops and the density drops. So see how well the predicted, doing mathematical modeling, how well it agrees with the data that we see. So the other thing I want to talk about, for every 4 protons that come together, one atom of helium is made, and notice that we get 2 neutrinos. Well, if that is true, then we should be able to see those neutrinos. Now, the problem is neutrinos are nothing like neutrons in that neutrinos pass right through matter. Neutrons do not. But so neutrinos have been really hard to kind of find. They're very, what we say, elusive. And so, you know, a variety of ways involving some really large-scale neutrino collectors and with some cool technology. But the point is that we are now indeed finding the neutrinos that we really think should be there. I mentioned large-scale gizmos and collecting neutrinos. Not only that, but buried deep underground. It's just an amazing sort of feat to catch this little elusive subatomic particle that does not interact with matter. There's been books written about missing neutrinos, so it's all good stuff.